So my background is pretty much this. I came to Microsoft in '96 after finally finishing my PhD at UC Santa Barbara, where ironically I worked on how to build kernelless operating systems, a project called Space. And then I came here and worked on the most widely deployed kernel on the planet, and for a long time managed kernel development for the platform independent pieces of the kernel. And more recently I've actually been working on how to get a lot more uptake in computer science departments. So some of the stuff I'll tell you today is stuff I'll go around and talk at universities in Asia, particularly Tokyo, but also schools like University of Waterloo, University of Washington I've gone to this year. And I really am amazed at how surprised students are when you start telling them about the internal workings of NT, and they realize that the only thing they ever heard about was Unix, and the only structure they understand is Unix. And when they learn that those aren't the only viable operating system ideas in the world, it's kind of eye-opening to them. And that's really our fault. That's why I'm working on my current project within Microsoft, is to change that, because we haven't been as open as we should have been about the great ideas and innovations that are inside the core of the Windows operating system.
Fantastic. Which is exactly why we're doing this. Perfect. Let me ask you though real briefly, how different are the two kernels? I mean, the overall core design of the two kernels, are they that different? Are they that different? I mean,
well,
it seems like the kernels have been the same for the past 20
yes,
years.
That's a very good point. And one of the things that I will talk to students about is how there really are only two operating systems on the planet that matter today. And those operating systems are Unix, which was started in 1973, and VMS, which started in about 1975. Well, the only version of Unix that's particularly important today is Linux, although Mac OS X and also Solaris attempt to hang in there. And the only important version of VMS is actually the son of VMS, which is NT. In fact, there was this long-standing joke. If you remember the HAL IBM thing about, add a letter to HAL and you get IBM. If you add a letter to VMS, you get WNT, or Windows NT. But I've asked Dave Cutler, who's the primary architect of Windows, and he says completely by accident. There was nothing intentional about that. So the history of the systems really does go back, and the amount of innovation that's gone in has been fairly significant for both Unix and for NT, but they really come from different kinds of backgrounds. One of the nice things about working on NT, just to say something about Dave Cutler, is that he is one among, he has no peers. He is the only person on the planet who's been the primary architect of three commercially successful operating systems. RSX-11 at Digital Equipment, and then VMS, which is a very significant operating system. It put virtual memory and 32 bits onto mini computers. And then for NT. And so it's been great working here. It's been great working on this team. But there are some really fundamental differences in the design, to get to specifically what you're asking about. And some of it has to do with how things evolved. In 1973, when they were developing Unix, they were working on very limited memory mini computers that had no sign of virtual memory. They were essentially looking at how to play a Space Wars game that one of them had developed on Multics and no longer had a Multics machine to run on. Whereas the system that we're building, and the reason that we started building NT back in 1989, is we realized that PCs were getting more powerful all the time. When we started out with the PC in the early 80s, the operating system wasn't all that important. What was important was the languages, the way that you could program it, the applications you could put on and make it do things. And in fact, the operating system was kind of an afterthought. And there's just stories out there, which I don't know which is correct, so I won't repeat them, about how we got into the operating system business at Microsoft. But basically, we needed an operating system for IBM to be able to use our basic software and our other languages tools to be able to make the PC be successful. But by the end of the 80s, it became clear that operating systems were very important. And so Bill Gates personally went out and recruited Dave Cutler to come and to start a team to build a new operating system, a platform for the future, for what ultimately became the Windows operating system. Now, one of the most interesting things about this to me is how long it takes for an operating system to fully mature into the mainstream. So Unix started in 1973, and I first saw it in about 1978, 79 with version 6. And the community really started to take off, I think, around 1979, 80 with the Berkeley distributions. And so this is for a researchy operating system used primarily by computer scientists at that point. And that took like 6 or 7 years to really take off. With NT, we were able to tackle something that the previous versions of Windows had not been so successful at, which was to get off the desktop and really start to take over primary server functions within enterprises. And so NT, particularly in NT4, was very successful at that. And that's the beginning of my history at Microsoft, because I arrived here the week after NT4 had shipped. And oddly enough for me, I actually had never run Windows in my life. I was a Unix guy through and through. I'd done a lot of kernel work. I'd done my own work on kernels, and none of it had anything to do with Windows. So in '96, I show up here in Seattle, which I love. I love working here. I love the climate. I love the environment. And I started working on NT5 in the first few weeks of when we started producing the NT5 operating system. And when that system then became Windows 2000, when we shipped it at the beginning of 2000, it was really an incredible accomplishment, because at that point, we had taken the server operating system of NT4 and really completed it in terms of a commercial enterprise operating system with the types of features you'd really expect. The next project was, how do we take that and make that the operating system that people use for consumer, for desktop, for those types of applications? And that became the XP operating system, which we released a couple years later. And so it's been a great transformation. I've gotten to see the end of it as we've moved off of a DOS-based operating system that was just there to support the applications into an operating system which is a fully commercial, high-quality operating system that gives great performance, a great set of features, a very rich operating system that really enables many, many kinds of applications and styles of communications. And the most significant thing for me is the ecosystem that Windows has been able to produce. So coming from the Unix background, it actually took me a long time to understand exactly what the business is here. And finally, when I understood it, it was really kind of amazing to me. We have created an ecosystem whereby hundreds and thousands of other companies and individuals working in those companies, and the tens of thousands, the hundreds of thousands of people have thriving businesses and thriving opportunities because of an ecosystem created by the Windows operating system and the Office applications, and those are really the heart, I think, of what Microsoft has produced. So that's been very exciting. Now, you asked me about the differences between the two kernels and the approaches to the two kernels. Starting back in '73, trying to run Space Wars and stuff, they came up with a very elegant system. You know, Dennis Ritchie and Ken Thompson particularly. It was simple. It had simple ideas. It was easy for computer scientists to use because the ideas were attractive and appealing. It had the idea of a fork for creating a process, which was very natural. Fork is not a particularly good idea in general, but in '73, in a swapping system, where you had to make a copy of a process to run another one anyway, because you had to swap it out to disk. You got the copy for free. It was a fairly elegant way of creating a new process. And then from the idea of fork to the idea of pipelines and the shell, being able to build these kinds of functions was actually, it was great. I loved it. When I started using Unix in about 1978, I just fell in love with Unix. I thought it was a great system. My real eye-opening experience came 1996, when I was finally going to finish my PhD after far too many years doing a whole lot of things. I was running a vice president of software at a startup company. I was doing lots of consulting, various things. I managed to probably tie the record for taking most number of years of my PhD. But finally, in '96, I was looking to graduate, and I realized that my children hated computers. Not a single one of them wanted to go into computers. And I trace this back to the fact that my pride and joy was a SPARCstation 1, a Sun box that ran Unix, ran the kind of Unix I love, not System 5, but BSD flavor of Unix. In '89, in their elementary years, they were trying to do their homework using things like VI or TeX or TROF. My wife was trying to do the minutes for the PTA, and we used to have interesting conversations because we had email. We had email long before most people had email at home. And she would call me up and say, gee, the email's not working. And since I was in graduate school, I didn't have 2 phone lines and stuff. So I'd say, well, write this down and then hang up, try it, call me back. And it would be things like /USR/LIB/SendMails-V- something or other. And she hated using computers. And then when I was finishing my thesis, I needed a way of presenting my results and talking about the work I had done. I got a cheap Macintosh, and I put like PowerPoint 5 on it or something, some very old version of PowerPoint. And my kids were using it to play games and things like that, and they just loved the software, and they loved to be able to write papers just by what you see is what you get. And we're sitting around the dinner table talking about what we should do, where we should move. And my third son says, you should go to work for Microsoft because they make really cool software. And so I started to understand very clearly then that the elegance and the ideas and the stuff I loved in Unix wasn't enough for an operating system to be successful. It has to be a system that people can really use that causes them to be productive and able to do the things that they want to do.
Exactly.
And it was a complete transition for me. And when I interviewed at another major company, it was a very large company back then, I had conversations that went like, how can we convince management to let us do these cool things that we think we'd really enjoy? I haven't had a conversation like that at Microsoft. Every conversation I've ever had has been about, in this vein, has always been about what can we do that gives value to our customers? What can we do that gives them a positive experience or fixes things that are wrong with the experiences that they're having now? How can we simplify the system? How can we make them more productive with it? How can we address the problems that they have? And so the customer focus, the end user focus that Microsoft has is something that's way beyond anything I ever saw as an engineer before I came here. And I think this is really why Microsoft has been so successful. In fact, what I tell people when I go to universities is I say that I see there being three pillars to Microsoft's success. One is the orphan microprocessor, because the x86 and the PC wasn't particularly loved by the people who loved Unix. It was sort of underpowered, and it took a long time for it to mature into what is now the dominant microprocessor on the planet. And so we loved the x86 before I think a lot of other people really understood where it was going. And so that was part of our success. Another part of it is our never say die attitude. This company has a vision that started in 1975, so it's like almost 30 years ago now. It was the vision of the power of computing to improve people's lives, to empower them to do the things that they wanted to do and be more successful. In fact, I think the early success of the PC was because people could take a program like Lotus 123, put it on a machine that they could afford, which is, about maybe 10 times more expensive than a PC is today, and be able to do things in their business or their endeavors and be far more effective at it than they were before. And this was the power that the PC was bringing to people, and it's the vision that we've always had. And so we've had this never say die attitude that says we want to accomplish that vision, and when we don't succeed, and there are a lot of things, we like to make fun of Bob in particular, but there are a lot of things that we haven't succeeded with at first, but we never say die because we know the vision of empowering people through computing is really important. And the third reason is because we've not targeted the elite of computing. So I went to a pretty good school, and I went to lots of research conferences, and there's a strata in computing which is very sophisticated. But most of the computing that happens, and it turns out, fortunately for us, to be most of where the money is in just the normal everyday type of programming that takes place in corporations. When I first became an engineer and started working for a computer company, which was Burroughs back in the 70s, it was COBOL and RPG were the big languages which really were the bread and butter of computing. And Microsoft has improved on that kind of environment, producing the Visual Basic environment, and now we're moving towards C# and the whole .NET technologies, which transformed that whole COBOL RPG world. In fact, they had trouble finding COBOL and RPG programmers for the Y2K bugs because it had been so supplanted by Visual Basic. And so that's the third, I call the third leg of our success, is that we've taken people who program for a living, who are more interested not just in the coolness of technology, everybody loves cool technology, but really in what they could accomplish and what they could get done with the system. Now, we made a great transition in moving from the Windows 95, Windows 98 era onto NT, because NT was, I sometimes get made fun of by some of my colleagues because I will talk about Windows 9X and as not being really the quality of operating system that we really needed to produce for our customers. And they would point out that it was actually very, very successful, which it was. But it really wasn't the quality of operating system that's needed to go forward with modern hardware and the types of demands that people make on computers. And so in the NT system, we built commercial level features. Things like ACLs, like a real security system, where you get isolation, where your drivers are run in a protected mode. You're not running them as an ordinary user as you are with the VXD drivers of Windows 95. We also have a system that fundamentally is architected very differently than, say, Unix. And so I'll draw you some stuff on the board presently, and I'll show you some of the differences.
Right.
Really talking about NT and then explaining how these things differ from Unix. I can't really say much about Linux because I've never seen a line of Linux source code, because Linux became kind of a fad after I came to Microsoft.
I would just like to point out that it should be clear that what an operating system really is at its lowest level is just is basically a hardware virtualizer. It's really that's what the core job of an operating system is, to virtualize the machine so that we can use it, and that we have created a beautiful, a powerful platform on which to then further abstract for people to write applications on, et cetera, et cetera. Now, do you want to sit down?
I'm going to write the board in there.
Okay. So exactly, how is NT built? What is NT? How is it structured?
Okay. Let me start by talking where you started a moment ago
Sure.
about what is it that operating systems do and what we need them to do. And so you're right that really what the operating system is the virtualizer of the hardware. And let's go back in history a little bit and talk about why these virtualizations were necessary and how they grew.
Okay.
So when I was in Santa Barbara, they had these big old IBM machines. And the model for how you use these machines is that you had a card reader and a printer, and you would load up what essentially was the operating system, which was the compiler, because they had no stake. They didn't really have any disks that had this on them, because these were very old machines from the early 60s, and they were cheap machines because this was a university. And you load up that, and then you load up your program on the back of it, saying Fortran, which is what most of them were written in. You put that in, and then it would crunch away at your computation after compiling it for you into memory. And then at the end, it would start to go on the printer, and you knew that program because you'd run it on different data sets before. You'd go over to the whiteboard they had, well, not a whiteboard, of course, but a chalkboard, and you'd see whose name was next and what their phone number was, and you would call them up and say, my job's almost done. Didn't matter if it was 2:33 in the morning because they had said they wanted to come in next. They would get up, drive in, and about the time you finished printing, they would put their job in. This wasn't particularly convenient. It wasn't particularly productive. And so what we started to do with operating systems was say, how can we virtualize that experience? One of the most important virtualizations is then the idea of multiprocessing. That can actually be working on multiple jobs at the same time. And so whereas I might have a processor, and before this is what I talked to. This was the heart of what my program ran on, was the processor. Now, what I wanted to have was the idea of virtualizing this into processes. And so a process is a virtualization of processor, which allows me to have multiple jobs run at the same time, and the actual physical processor is shared. Now, one of the differences between NT and Unix is that Unix said the process is the fundamental way of sharing the CPU. But that was an idea that came before virtual memory became extremely common. Because what a process is, and what a process is, and I think VMS is the same way, and also NT, is a process represents what I will call an address space. It's commonly called an address space. This is essentially this, that you have some kind of mapping that says when your program says I want to access some variable, the mapping says where is it stored. In other words, this is your RAM, this is your physical memory, and this is kind of a virtual memory that your program operates on. Now, these are very tightly associated with the idea of a process, because a process determines the address space where your program executes. But the actual execution of your program, even though it's in the context of a process, it's really something different. So I'm going to erase this part so I can keep drawing down the page. And so within a process, you end up having this idea of threads. And so a thread is the actual sequence of execution that takes place in your program. It executes in the context of a process or a virtual address space, so it is able to access memory, but the threads correspond more directly to the processors. The processes actually correspond more to the MMU, the threads correspond more to the CPU. The reason this is an important idea within the VMS system and then with the NT system is that you don't have just a single processor anymore. You have, processor 0, you have processor 1, processor, and you like all these processors to be able to work in your same application at the same time. And so by separating out the threads, which represent the CPUs or the processors, from the idea of the address space you work in, which is usually associated with an application, you're then able to take better advantage of the processors. Now, Unix is able to do this by creating multiple processes because they correspond to the processor. You have to do more work to figure out the sharing. It's a little bit more difficult to cooperate. And so even Unix has come around to this point of view, incorporating actual real threads that operate underneath the processes.
How is this changing with multi-core processors?
It's becoming more accessible. With multi-core processors, it now means that basically within a few years, everybody will have multiple processors that they're operating on. So this picture here, which for most people is unusual. Most people don't actually think they really have multiple processors today because those machines are more expensive and so they don't buy them. But when multi-processors come on the same chip, what's called multi-core chips, they have CPU cores, multiple of them on the same chip, everybody will be experiencing multiprocessing. But it's actually true today that on the higher end chips, particularly from Intel, they actually get sort of part of two processors. It's something called hyperthreading. So when you read about hyperthreading, the operating system pretty much treats these as if these were separate processors. But the truth is that, and they're paired. So there's processor 0 and 1, processor 2 and 3. And what happens here with the hyperthread, we call it HT, is that a lot of the resources on the CPU are shared between the two processors. And so when you're running two different threads on the two processors, hyperthreading means I can run those two threads at the same time, but they'll get in each other's way a little bit because I'll have to stop and wait for some of those shared resources to become available. So one thread's making progress, it uses, say, some part of the ALU or does some floating point. The other thread suddenly needs to do floating point. It has to wait until the first thread finishes. With multi-core, I don't have that sharing, and I essentially get two full processors that are able to carry out the execution of threads independently.
Sure. But way up in the abstraction, up in programming land, with multi-core, you have to actually know how to program in a multi-threaded way correctly, which very few people know how to do. Now,
Right.
kernel guys like yourself, you live in the world of concurrency.
Right.
It's not a big deal to you, but you are very rare as far as your skills.
Yes.
So for the people way up above, it's a major, major problem that multi-core is now bringing in terms of being able to get maximum out of that CPU. You really have to know what you're doing. And it's not
Yes.
easy to write multi-threaded code.
Yes. Now, I would totally agree with that, particularly if it was around the time of my performance review. I would completely buy into the argument pitched to my boss that yes, I was an extremely rare animal and that what I was doing was very specialized and I was worth a very great increase in my salary. Unfortunately, Microsoft has really pushed forward a type of style of programming which has made it necessary for most programmers who are not doing very simple applications at least. Most programmers who are doing system types of applications to now become very familiar with multi-threading. And there's several reasons that this is true.